Today we're going to be talking about continuity at a point. So consider f of x on the domain of, we'll say, a to b. Okay, we'll even include a and b. So consider f of x on the domain a to b. The function f of x is continuous at c, where a is less than c, which is less than b. Basically, it's in between a and b, but not equal to either one. If and only if the limit as x approaches c of f of x is equal to the actual function f of c, the function evaluated at c. Also, is continuous. Is continuous at a if the limit as x approaches a from the positive side of f of x is equal to f of a, and then likewise b from the negative side is equal to f of b, would be continuous at b. So basically those are continuous at endpoints. Example of one of these would be, for example, the limit, or not the limit, basically the question is the function f of x, is the function f of x equal to the square root of x continuous at x equals 0? And the answer would be yes. It's simply because the limit as x approaches 0, right? The limit as x approaches 0 from the positive side of the square root of x equals 0. However, the limit as x approaches 0 of the square root of x does not exist, right? So the limit does not exist because, note, the limit doesn't exist because we can't actually even approach from the negative side, but we can approach from the positive side because that is in fact part of the, that's part of the domain, but it's an endpoint of the domain. And so since it's a border of the domain, you have to approach just from one side, but that does mean that it's actually continuous. So it is continuous at 0, which is interesting. Okay, so that's continuity. So that's the definition of continuity. We have a number of different discontinuities. Let's go over all the different types of discontinuities, right? We've actually already talked about them. So we have jump, right? Jump discontinuity is when we come in from one side and then we leave from another, like that. There's removable, which is zoop, zoop. There is a infinite discontinuity. That's the one where it goes up to infinity, like that. That's infinite. And then there's so those are probably the three that you have already talked about, or already know. There's one more that I'm going to talk about, is oscillating. And oscillating is one that, as it gets closer to something, it oscillates faster and faster and faster, and then as it goes away. So the example here the function would in fact be sine of 1 over x. That has an oscillating discontinuity at x equals 0. As I get closer, I mean, you can graph it on your graphing calculator. You'll see basically as it approaches 0, it starts to jump back and forth faster and faster and faster. And so by the time you get to 0, it is jumping back and forth an infinite number of times in between 1 and -1. And so you can't possibly have an idea of where it limits out to. So this is actually a oscillating discontinuity. So that's good. Excellent. All right. By the way, a couple little notes on continuous functions. Let's see. Yeah. So let's do something else though. F of x is a continuous function if it's continuous for all points C in the domain, and f of x is continuous on an interval if it's on the interval, well actually, on the interval a to b. If it's continuous for all c inside of a to b. And and we'll put and continuous at the endpoints. So we'll say that too. That should probably work out pretty well. So that's kind of your continuous functions. Continuous functions have no discontinuities in them. Continuous on an interval just means there's no discontinuities on that interval. By the way, if f and g are continuous, then so are f plus g, f minus g, f times g, that's good, k times g, where k is a constant, and f divided by g, where g does not equal 0. Good. All right. So that's pretty excellent there. And the last one is let's see. Yeah, no, that's good. Perfect. All right. Okay. Lots of little notes today, huh? All right, last thing, I'll put a little line there. All right, another little note. I'll post all these notes on Canvas for you as well. The intermediate value theorem is basically, the idea is if f is continuous on the interval a to b, then then for any value between f of a and f of b, there any value there exists a c for any value between there exists a c in a to b where f of c is that value. Basically, this should make sense. Graphically, what am I saying here? I'm saying that, okay, so here's our function. Here is a. Here's f of a. Here's b. Here's f of b. Well, what I'm saying is that at any point, pick any point, any value here. Let's just say I want to pick this value, right? And I'm going to say, well, so if I pick this value right here, there has to be a point on the function. Namely, there has to be a c such that f of c actually hits that value. So if I want to pick this value, that's in between, somewhere in between f of a and f of b. So if I pick this value, well, there's got to be some sort of c such that that value actually lies on the function. In other words, if you're, if you go on a 5-mile hike, at some point you have to cross over mile 4, or at some time in that afternoon you have to cross over mile 2. Like you can't just make these weird leaps. That's all. That's the intermediate value theorem. You have to hit every value along the way. So that's just like quick note review. I'm also going to do a little video on just example problems and things like that. But that's just the notes for today. I'll also post these notes on your Canvas page. So.